Hi, everybody. This is Jeremy Levy from PQI, and we have a special segment we call a Quantum Breakdown, in which we discuss a paper that's published by our members. And today I'm joined with Peyman Givi and Andrew Daley, who are, I would say, like founding PQI members. Andrew Daley is at University of Strathclyde in Glasgow. Peyman Givi is in mechanical engineering at Pitt. And they are the first two authors of a NASA technical brief, which is called Quantum Speedup for Aeroscience and Engineering. So first off, thank you, Andrew and Peyman, for joining us this morning and this afternoon.
It's a pleasure. Thanks, Jeremy.
Oh, my pleasure.
Maybe you could just give some background about like how all this came about.
So I guess from my point of view, I mean, there's a historical discussion around the project that we started all the way back now in about sort of 2012, when we started sort of talking about bringing together physicists and people from aerospace engineering to ask what you might be able to do with quantum computers in the future that would be relevant for computational challenges in aerospace. And we had some initial ideas, and we've written some papers. It's been a really fun sort of learning curve as we tried to develop a common language that we both understood. So Peyman and I, and then sort of the broader members of the team, including Jeremy, of course. And of course, we have a couple of joint publications that came out of that, looking at quantum algorithms and applications for particular computational challenges that Peyman and his team face every day in their sort of computational fluid dynamics and combustion problems. From my perspective as a quantum physicist, someone who develops implementations of quantum computing and also looks at potential future applications, this whole thing of starting to interact with people from other fields, both academics and then also people from industry in very different areas, learning about their computational challenges, and then sort of trying to understand what quantum computing might be able to do for that field, I think is very exciting, both because it allows us to learn more about the challenges, and also because the way that quantum hardware is developing has been very exciting, but probably a general purpose, large scale error corrected quantum computer is still a little way off. And I think that the most exciting possibilities for the coming years are taking maybe special purpose problems and finding ways to implement those in maybe hardware specific ways to solve relevant problems, you know, probably on a much faster timescale than you'd have for general purpose quantum computing. And that requires not just people who know about quantum computing thinking sort of in a vacuum, but really, you know, building bridges to other communities, getting expertise in on what the problems are and what the potential ways of solving those problems might be, and trying to match that with the hardware and software knowledge that we have in quantum computing. So for me, this was about, you know, making contact with people in aerospace engineering, and the review article is about trying to provide a background for what quantum computing is, what the possibilities might be, to start the discussion with a broader base of people from that community. I have to say it's been a delight working with Peyman and his colleagues over the course of the last few years. This particular technical manual came out of a conference that Peyman organized. And it's been great to see the enthusiasm with which people from that community have embraced the opportunity to learn about what we're doing, the same as we've had an opportunity to enthusiastically learn about what their computational challenges are. So from my perspective, that's sort of the background and the goals really of what we've done here.
Yeah, thanks, Andrew. Yeah, so Peyman, what was, you know, your journey was a little bit different, right? I mean, in some sense, you were not really quantum before, and you became quantized, and you know, Andrew, of course, had a big part in quantizing you. So how do you see that experience as sort of like generalizing? Like how can, in some sense, this was really a little bit ahead of its time, right? This idea is now a lot more people are thinking about how future or emerging quantum technologies may be relevant to them, what are the things that, that you would learn, or you would like advice you would like to give to people, other people who may want to see a quantum angle in the big challenges of what they do?
I see. Well, as you know, in aerospace engineering, we are pushing the limit of high performance computing. If you look at the nation's supercomputers, the large amount of them are being used for problems in computational fluid dynamics, in combustion, propulsion. And the problem of turbulent flow and turbulent combustion is one of the most challenging, most computationally intensive problems. So as you would see that my colleagues are in CFD, in fact, some of the other co-authors of this NASA technical memorandum are two of the leading CFDers in the world, one from NASA Langley. And what the Department of Defense and NASA and others, they wanted to say, okay, we are pushing the limits of classical computing. But as you have mentioned it yourself, and we have reached already, the end of the linear progression of supercomputing. So what is the alternative? What are the alternatives? Of course, as you guys know very well, quantum computing has been considered as one of the possible ways of dealing with that problem. But the fact that it doesn't exist there, and the fact that engineers don't want to spend time on things that is proven, that made it difficult to bring it into engineering for practical calculation. But the thing that we did at PQI, which I thought was very, very productive, was that we said, okay, well, maybe we don't have a universal quantum computer yet, but there are algorithms being developed, and these machines are being built. Maybe some of the other quantum simulators are being made. What kind of problems can we tackle? So what kind of, that will require us to talk the same language. So when I came, to our physics department, and talk about this problem, just we had to get familiar with each other's terminology. And the good thing, with the physicists, you guys know all the field. For us, we know very little. So I had to learn about quantum, about what is quantum, what they can do. And I'm really grateful to Andrew, who was really patient, teaching us, weekly teaching about basics of quantum physics and quantum mechanics and quantum simulator. And throughout the discussion, two things we found out. One thing was that, well, there are many algorithms right now that we can demonstrate it has advantages in classical problems. If you use this for combustion or turbulent mixing problem, the algorithm could be, very, very useful. And the second thing we learned is that there are a lot of quantum-inspired algorithms. There are some quantum, things that coming from quantum physics, quantum calculation, quantum algorithm, but could be used for classical computation. And those things can be used right now for some practical calculation. That's the kind of research they're continuing now. So I just think that, the lesson learned in this multidisciplinary, if you're lucky enough that you have experts near you, you have to, go to them and start the collaboration and learning from them. And that, I think that was the advantage we had at PQI.
So there, been a lot of announcements from companies, like IBM, D-Wave, and so forth, and they say, we've got these great, quantum computers, we've reached quantum supremacy, and so forth. So I think for a lot of people who are maybe casually following the field, it's hard for them to understand why those computers quantum computers aren't already being used, in your applications. So is there, maybe you sort of alluded to some of the issues, but I think there is some maybe a blurriness or fuzziness about what exactly we have right now and what we need in order to, and maybe these are things where you have people digging from opposite ends of the tunnel, right? Where you make adjustments to you relaxed some of the initial assumptions that you thought you needed for a fully error-corrected, large-scale quantum computer. Maybe there are certain things that you can still do if you don't have all of the pieces together, and maybe there are adjustments that one can make to the algorithms. But the question is, given what we have right now, I mean, are any of those quantum hardware platforms useful for current problems, or are they useful in terms of research, in terms of being able to at least explore how problems scale or how they might scale in the future?
So it's a great question. And I mean, I think the first thing I should say is, I mean, look, obviously there has been an enormous amount of progress in development of quantum computers, both in industry at places like Google and IBM, Rigetti, Honeywell we've heard about recently, and some great startup companies around the world using different technologies. And also, I have to say, in university labs in a number of different platforms. And you see that again in very many countries around the world. So it is a very exciting time because the hardware is getting to the level where you can start to do things that are useful in terms of understanding where we might be able to go in the near future. There's a big difficulty, and again, thinking of sort of a general audience here, there's a big difficulty in programming a quantum computer, because you can't just take the algorithm you'd run on a classical computer and say, I'm going to take that, I'm going to run it on my quantum computer and get some sort of advantage. Really using quantum mechanics, the strange properties of microscopic objects to do the computation requires normally doing the computation a very different way. This is actually where some of these quantum-inspired algorithms come from. You think of a different way mathematically of solving the problem than what you might have used in the past on a classical computer. And in some cases, that's shown to actually give an advantage even when you implement the quantum algorithm on a classical computer. But the point is that you need to find new ways of programming it, which means that you need to understand the problems you're trying to solve and understand where the hardware can give them an advantage. So I think that your analogy of the tunnel, I hadn't thought about it like this before, but I think it's a relatively good one. People are digging from one side in the sense of building the bridges between the practical problems you want to solve and the hardware that we've got now, improving that hardware, reducing the error rates, developing the level of controllability, developing the number of qubits and the length of time that you can realistically run a calculation for before it's dominated by errors. On the other hand, we're trying to find new ways to take problems that are computational challenges at the moment and adapt those so that we can make use of either a generic quantum platform or indeed properties of individual implementations of quantum computing, which might be programmed in a slightly...
So we're back after a commercial break with Andrew Daley and Peyman Givi. Thank you both again for joining us PQI today for this PQI breakdown. So really what we were talking about, I guess, was like this kind of effort to, to reach, like, to actually make a connection and to do something useful. And so, I mean, ultimately, right, that's the goal is to develop quantum hardware that can deliver the kind of speed up or take us beyond what we what is the current state of the art, with classical computers. And clearly, even quantum inspired algorithms are seemingly useful for breaking out of maybe intellectual rut in terms of solving some of these great challenges. So I guess what I was wondering was whether there is active research to work on the specific, let's say, the algorithms that you've already developed to see if in small versions they can solve, little baby problems, or whether they're whether it's still a little too far away in terms of the current hardware.
So I think we're getting close for a number of things for demonstrators, certainly for, as you put it, baby-sized problems. And I think that there is, I think it's very realistic that at least on the level of special purpose quantum computation for analog simulators, for example, that we might be able to start applying these to material science related problems in the next few years and see what, you know, I and a few others would like to term a practical quantum advantage, which I think is what you're talking about, a situation where you take a problem that's interesting for a particular academic field or for industry and really see, you know, a computation on quantum hardware that performs better than any known classical algorithm. And I think that that's quite realistic, particularly, as I say, in these material science simulations, maybe time dependence of things that are Hubbard model type problems that people address in industry, also for development of battery cathodes or industrial catalysts. And there's been, of course, a lot of things done in recent years on optimization and on, you know, related to that sort of variational quantum simulation and variational quantum computation. One of the difficulties there is to really identify the point where you definitely get a speed up over anything we know how to do on a classical computer. And in fact, I would say that these quantum inspired algorithms have actually been consistently raising the bar for what you have to do on a quantum computer. This, of course, is not bad. For me, this is a good motivation for people from other fields to engage with the potential for quantum computation, because you might just find that you get a speed up that comes before the quantum hardware reaches the level of maturity to really solve your problems. But I think for certain specific problems, we're getting relatively close with these things. And of course, companies and research labs around the world are very keen at the moment to engage with people from very different communities to try to identify what the best candidate problems may be in the coming years, you know, as those, you know, baby step problems to show where the scaling is going, or maybe even to show a genuine advantage over anything people can do on a classical computer.
So, so maybe you can explain also to our, you know, to our members, like how and why, like why NASA is interested in this. Is this maybe part of a long-standing interest in, you know, developing algorithms and maybe technology for solving, you know, complex problems related to their mission? What is their long-term vision or goal in this field?
But, you know, first of all, you know, transition going from classical to quantum computing, you know, it is really nothing that we haven't done before. I mean, we haven't gone to quantum, but, you know, at any stage, going from any kind of calculations, going from vector machines to parallel machines or whatever, there is a curve that you have to learn. Not going to GPUs, from CPU to GPUs, there's a thing to learn. So going to the quantum computers as well, it's going to be that way. I mean, there's going to be, you know, we have to learn the new programming, new orientation, new software, you know, so this is the transition we all have to go. So NASA, like any other agencies like DOE and DOD, they're all more interested to know about the subject. I mean, there is this potential there out there. So they would like to know what kind of problem they can be solved by this new technology. Well, at NASA AIM, they already have some of the quantum simulators like D-Wave and others, and they're solving some of the problems in machine learning optimization, because it comes from, you know, from linear algebra, solving system of equations. So they're already the engineers that the people who are doing computational fluid dynamics and others, they are involved with those computations. At other NASA centers, they would like to know. I mean, so that was the reason, you know, about a year or so ago, NASA asked us, you know, since they know we had this program that we want to deal with aerospace problems, to organize a conference for them, to invite people like you guys, you know, like the quantum expert and people from, you know, the computational fluids and combustion, to see what are the prospects of this thing for the future. You know, when these things are going to be developed. So there is a lot. I mean, NASA is one of the places that they do the heaviest computation. So they're always looking for possibilities of enhancing their computation. So that's what they want to know about this. And that's what they're very much interested in publishing this report.
Right. So what advice would you give for a colleague, let's say, from PQI, who is, as they might say, quantum adjacent, right? They're kind of like on the outside looking in, and they want to know, how they can really stick their toe in the water, right? And they say they're working in a different domain, right? First of all, how would they know whether there really could potentially be a quantum advantage in their domain of knowledge and inquiry and so forth? And let's assume that there is something that is related to information processing, something that is a big challenge, analogous to what where you were 8 years ago. The question is, how would they go about seeing whether there could be something useful, and how would they go about taking steps in that direction?
Jeremy, I really don't think there is any other way of doing it except talking with the experts. I mean, there is, in any kind of in field that are so across disciplines, I really do not see any other way that, you sit down with the expert and learn from them, on both ways. So one of the things in here we had to do to learn to talk to each other. We had, numerous meetings at PQI, and then when, at the StratQuai, that, we had several meetings there, and here, just brainstorm what kind of things we do, what they do, how we can, put my problems in the language they could understand. Some of Andrew's students who are doing in quantum, talking with us, knowing about the mixing algorithm. I mean, I think to begin with, I do not see any other thing except to be talking with experts and learning from them.
And so I totally agree with Peyman. And whether there's going to be a quantum speed up in a particular area or not is generally a research question that you need to ask. But the first sort of step is to develop a common language and to explain in two directions the things that you're trying to look at. And I think that most people who are interested in developing quantum algorithms and who know more about quantum computing are fascinated to learn what the challenges are in other fields. I think it's so mutually beneficial, and just on an intellectual academic level, it's so fascinating to learn about the things that are being done in other areas. But I think most people would be delighted to engage with people from other areas. And of course, this goes for the PQI, where you already have a forum sort of set up to try to exchange ideas, people from different disciplines. But if you are somewhere where you don't have direct access to that, just go and talk to people in your physics department. Find out who might be interested in talking, because I think that there are lots of interesting opportunities in the coming years if you can develop that sort of that joint language. And again, I think it's a fantastic thing to have an opportunity to learn about what's going on in other disciplines. I know I've really enjoyed learning from Peyman and his team.
Yeah, I think I'm really heartened, by your answers, and I totally agree with them. That it's really, in some sense, there are a lot of sort of new challenges that show up when either when you're trying to build a quantum computer or apply quantum algorithms to new problems. You're forcing yourself to think about what you do, what you've been doing in different ways. And that can be unsettling in the beginning maybe because people are talking in a language that you don't understand. But then once it begins to click, then you realize that, well, wow, that there are these huge opportunities out there. And I think that's what I think people are finding more often than not, is that there are opportunities for quantum speed up that were not recognized before. And those are opportunities that, are exciting and can help define research directions for years and maybe decades to come. Well, I think this has been a great breakdown, and I hope that our colleagues will take a look at this and try to see, maybe by analogy, how even if they're not, let's say, working themselves in the aerospace industry, to at least understand how it's possible for this new field of quantum information science and technology, that it could be applied to areas that weren't obviously applicable, where it wasn't obviously applicable before, and maybe get inspiration for their own disciplines. And so, yeah, I want to thank you for writing this article and making it accessible to other other groups outside of the specific domain of knowledge. And yeah, I want to thank you also for your time this morning and this afternoon for joining us at this PQI breakdown.
Well, thank you, Jeremy.
Thanks, Jeremy. It's a pleasure.